Hello everyone and welcome to another Physics 211 lab simulation. This week we're going to be talking a little bit about light diffraction, and unfortunately we're not going to get to spectroscopy this semester just because we found that it was a bit too challenging to ask you guys to do it online, so we wanted to do something that was a bit more manageable. In any case, before you jump into this lab manual or this lab video, please make sure that you have read through the lab manual as always before you watch the video, just because that way you have an idea of what's going on before we jump in here. So, that said, let's jump in. Light diffraction is a phenomenon that happens wherein if light hits a wall that has like a gap in it or something like that, it will interfere, or it will cause these wave patterns that interfere, and if you measure the intensity on some screen some distance later, it will actually kind of look like this nice little wavy thing, as long as you have set up your experiment sufficiently nicely, which we are going to do today. So there are going to be a couple equations that we're using, and first of all, that's going to be this equation here. The tangent of theta is equal to the distance y over the distance d, where the distance, capital D, is the distance between the slit itself and the screen that you're measuring the light from. The distance y is the distance from the central maximum, so this one right here, and whatever maximum you are currently looking at. And that determines what the angle between the normal of the slit and the maximum that you're currently looking at. So we'll be using that equation there, and we will also be using the equation, the sine of theta is equal to plus or minus m lambda over d, where m is the number of the maximum that you're looking at. So I can explain that real quick. So the central maximum we call m equals 0, which should make sense because if you take the sine of, it should make sense because there is no angle between from the normal, in this case, from the maximum, the central maximum, right? So we call m equals 0 for the maximum, and we just use integer values to describe the rest of them. So that you can see there's a little peak right here. So if we were to measure from the center of that peak, that would be m equals 1. So that's that m value. Lambda is the wavelength of the light you're looking at, so of course we know that different colors of light correspond to different wavelengths, and that is described by lambda here. D in this case is just the distance between, or is the distance between the gap distance of your slits. And finally, again, theta is the angle from the normal of the peak that you're looking at, so, or of the central peak here. So the angle, like this angle right here, right there. And I think that's everything as far as variables are concerned. I will get into how to make those calculations a little bit. I will not physically be doing the calculations for you because I'm just here to take the data for you, but I will explain how to make some of those calculations as we're going. So let's jump into the lab procedure here. It says to click on the following link, which I've already done, and to select the wave interference option. So we're going to go here, and it says to check the laser option, the screen option, intensity option, and the two slits option. So you can see we have ourselves a pretty nice looking experiment here. And just to give you an idea of what's happening, if I just send some green light, you can see these laser pulses of green light come, they hit the screen, and they start constructing and destructing, they hit the slits and then they start constructing and destructing in the space between the screen and the slits. And then here's your screen, and you can see the spaces that are dark correspond to the minima, and the spaces that are bright correspond to the maxima, as you can see on this graph. So when there's a valley, it's dark, and when there's a peak, it's bright. And these peaks are going to correspond with the whole integer values of m that we were talking about. So this would be the central maximum, so we'd call that m equals 0. This would be called m equals 1. And then the distance between these two things is what we would call y. Okay? So let's jump in. And it says to, once you've done all of that, to pick a color of light using the slider bar. So I'm going to turn this off. And I'm going to pick blue, because blue is my favorite color. And go ahead, if you want to follow, if you want to follow and take measurements with what I'm doing, go ahead and record blue in the color 1 section here, and then we can jump in. So it says to move the slits to the left side of the screen in step 6 here, and to click the green button to get things started. So again, laser pulses coming in, they're going to construct or deconstruct, and once they hit the screen, you'll see the pattern kind of emerge here. All right, so it looks like our central maximum is pretty much right in the middle as it was before, and the first maximum after that one is over here, and this could also be called m equals 1 over here. So use the tape measure tool on the left side of the page and measure the distance on the screen between the central maximum and the first peak. Okay, so it actually looks like it's on the right side. That's all right. Notice quickly that the units of distance that this tape measure is going to measure in is in nanometers. So make sure that you convert to meters when you're doing all of these calculations that you'll be doing, and make sure that you don't call what is actually 1500 nanometers 1500 meters, because it is not that. So what it says to do is measure the distance between the central maximum, m equals 0, and the first peak, m equals 1, above or below that. So I'm going to place the tape measure right along the line of the central maximum here. There we go. And I'm going to measure the distance between that and the first maximum, which I think is about right here. Let me double check. Yeah, that looks pretty good. Let me just pull this back a tiny bit here. And move this forward. All right, that looks good to me. So as you can see, that's about 1,354 nanometers. So 1,354.4 nanometers. Now go ahead and record that in the data sheet where it says y here. And that's going to be the distance between the central maximum and the first maximum, which we are calling m equals 0 and m equals 1, respectively. Now, do keep in mind that, as you can see, these maxima are kind of wiggling around, and I'm using a tape measure, which isn't the perfect measurement tool, right? So there's going to be some error associated with this. When we go to calculate the wavelength of the light that we have here, which ostensibly is blue, and you can look up the value of lambda for blue light online, we're probably not going to get the exact same thing as the expected value, and that's okay. That just means that there's some error in this experiment that we really have to take into account. So when you go to talk about your data and you say, oh, I measured something that was 50% different than the wavelength of blue light, even though I was using blue light, go ahead and explain that and make sure that you just understand that this is not a perfect setup because we're using tools that are imperfect. Now, the next step is to use the same tool, so this little tape measure here, to measure the distance between the screen and the slits. So here's the screen, going to go to the front of that, going to measure the distance from that to the slits, to the very front of the slits, and I'm going to make sure that it's about as level as possible, because you don't want to be measuring the hypotenuse of a triangle. You can imagine like this distance is going to be longer than this distance, so make sure that you try to make it as flat as possible. So once I place that there, and you can see it's about 4,420.3 nanometers, so go ahead and mark that down for capital D in color 1. And then finally it says to measure the distance, the gap distance of our two slits. So they should be the same, but we're going to measure both just in case. So it looks like I've got it about on the edge of that one. Oh, come on. There we go. And I'm going to bring it up to the edge of this one here. And, okay, great. That looks to be about 526.1 nanometers. So go ahead and mark down that for the distance lowercase d here. Again, that's 526.1 nanometers. And then I'm going to make sure that that's the same distance as this one over here. Okay, so yeah, that's pretty close. Good. So now we've done everything in this table for this column except for calculate lambda. And I'm not going to do that for you, but I will walk you through how to do that. So first of all, what you want to do is calculate lambda. So you need a few things for that. You need lowercase d, you need the value m, and you need theta, so that you can take the sine of theta. How do we do that? Well, theta is going to be the inverse tangent of, the opposite over adjacent of the thing that you're looking at. So in this case, opposite is going to be the screen distance. So that's going to be capital D. So you're going to take the inverse tangent of, or the arctangent, whatever you prefer, of D over the position of the first maximum, and that's going to be the adjacent. So you're going to hit the inverse tangent or arctangent, whatever you prefer, of D over Y. Again, that's going to be capital D over Y. Take the inverse tangent of that. That will give you your angle, theta. And then you can plug theta into here and solve for lambda. So, multiply by D, divide by M, which in this case, M is just 1. So actually you can kind of forget about M here, but if we were to go to, other maxima or minima, you would need to adjust for what M would be. But in this case, it's just 1. So, multiply by D, and then multiply, and then take the sine of theta to get lambda. And it should be relatively close to the value to the wavelength of blue light. But, if it's off by a bit, that's fine. Just make sure you explain that. All right. Now it says to repeat steps 5 through 10 for a different color of light. I'm going to choose red because I like red. And I'm not going to move the slits or the screen or anything like that, or adjust the distance between the slits. So actually what you can do here is just go ahead and write down name of color, red, D is the same as before, and lowercase d is also the same as before. I'm also going to remeasure the distances just so that I can have an idea, just to make sure that I made an okay measurement before. So let's see here. Okay, I got about 4,410.5 nanometers for D. So you can go ahead and mark that down in here if you want to, or you can take the average of those two measurements and plug it in. Totally up to you. And I'm going to remeasure the slit distance real quick before we get started. Alright, that looks good. And we get about, oh gosh, we get about 497.1 nanometers. So again, relatively close to what we had before. If you want to take the average of those two distances and plug them in so that you get a slightly better measurement, go ahead. And then we will continue on. Now it says to use the tape measure tool on the left side, or just the tape measure tool, to measure the distance between the central maximum and the first peak. So here I'm going to place it on the central maximum, which I'm going to call this one. Again, this is m equals 0. And now I'm going to measure the distance from that to the first maximum. And again, it's wiggling a lot, so it's going to be hard to find the exact point, but that looks to be about it. And here I measure about 2007.1 nanometers. So you can plug that in for y. Again, that's 2007.1 nanometers. Go ahead and plug that in here. And then you can calculate the measured value of the wavelength of red light. I will walk you through that once again. So what you're going to do is take the inverse tangent of d, capital D, over y, which we've just measured here, and then choose m to be 1, plug theta that you just calculated in and calculate the sine of theta, solve that for lambda, and that will give you the wavelength, something close to the wavelength of red light, hopefully. Now again, if I've made extremely imprecise measurements and you get values that aren't super close to the wavelength of red or blue light, that's okay. Just make sure you explain it in your data analysis section. Say, hey, my data told me that I got the wavelength for something that was more like purple light. That's totally fine. Just explain it in your data analysis and understand that the tools that we were using for this are not exactly perfect. First of all, these are kind of wiggling a lot. Like we could have maybe set up a scenario where the maxima and minima are more stable and then found the exact peak value. And we could have used a more precise measurement tool. So if you want to use those as some of your error sources, feel free to do that. And then go ahead and make sure that you do your lab report. You have your theory and your intro. You show the data, which is just in this case going to be this data table here that you filled out. And you do some analysis on that data, look up, answer these discussion questions, and then make sure you have a conclusion as well. And we will be all good to go. All right, well, thanks again for watching, and have a wonderful week.